Great. Well, welcome back everyone to another exciting session of CE 397 Control Theory for Smart Infrastructure. Let's go ahead and get started. So last time we gave an overview of LTI systems. Who remembers what LTI stands for? Great, linear time invariant. So we had an overview of LTI systems. We looked at continuous versus discrete LTI systems, and we showed how we could formulate LTI systems for different civil engineering problems. So I formulated LTI systems for a structural system. We described the structural system in terms of a differential equation using Newton's second law. I formulated the LTI system for a LRC circuit using Kirchhoff's laws for voltage and current. And we found that the actual form of those differential equations were almost the same. And I gave you a little bit of a preview about what the response of those systems will look like, right? We saw that the response of that LRC circuit is going to be very similar to the response of the structural system. But what I didn't do yet is tell you how to solve LTI systems, how to solve differential equations that are linear in continuous time. So today, that's exactly what we're going to do. I'm going to show you how to solve LTI systems, so how to solve a linear differential equation of a single variable in continuous time. I'm going to show you how to characterize the response of an LTI system. So we hinted at it last time, what the different responses will look like. Today, we're going to provide more detail on how you can characterize the response by looking at the terms of the characteristic equation. In particular, I talked about last time how the roots of that characteristic equation determine the response. Today, we're going to show exactly how that works, okay? And finally, we're going to talk about different types of solutions to LTI systems, in particular, homogeneous, particular, and complete solutions to LTI systems, okay? So after today, you should have a pretty good understanding of how to solve LTI systems, at least for the homogeneous case. I'll talk about what that means in a little bit, but this is a good refresher on solving differential equations, okay? So if you feel like you still need to catch up a little bit, this lecture is going to help, okay? Okay, so let's talk about LTI systems and how to solve them. Okay, so quick recap. Okay, last time we stated the standard form for an LTI system of a single variable in continuous time. So let's consider the nth order LTI system. This is going to be just our generic LTI system. We stated the standard form last time in class. This is the standard form for which any LTI system can be expressed. I'm going to write it a little bit differently this time for the purposes of this lecture. I'm going to write it like this. So we'll start with our nth order derivative of the output y with respect to time, plus a n minus 1 times the n minus 1th derivative of the output y with respect to time, plus ... all the way to a1 dy by dt plus a naught y is equal to our input u. Okay, so what's different about how I wrote it this time, by the way? Does anyone remember? Right, so one difference is that it's only first order with respect to u. So we're only considering just a single input and not its derivatives. What's the other difference that's a little bit more subtle here? So the order of the derivatives should be the same. What about the first term here? Right, so all I've done here is that I've monetized the standard form. So I divided by the coefficient a sub n. Okay, and that will just kind of facilitate some of the discussion today, but note that this is now now monetized. So there's no coefficient on the highest order term, it's been divided through. Okay, so just a difference to note. And recall, we can express this system in operator form. Okay. We can write the system as follows. We have that our output yt is equal to some operator LP applied to our input ut. Okay, and our operator LP we have described as this rational function, this rational polynomial in P, which is our operator. Let's write it as 1 over P to the n plus a n minus 1 P to the n minus 1 plus ... So this is just the characteristic polynomial of this LTI system here, all the way to a naught. Okay, so these are two alternative ways that we can express our generic nth order LTI system, or generic nth order linear time invariant system. Okay, and remember that this denominator here, we called, what was our name for this, for the denominator of our operator L? Do you remember? Right, characteristic polynomial. So this is an important, I ran out of space here. Characteristic polynomial, very good. And it's called the characteristic polynomial because it contains essentially all the information you need to characterize the homogeneous response of the system, which I'll talk about what that means in a little bit. But remember that the roots of this characteristic polynomial are going to play an extremely important role in determining the system's response. Okay, so just remember that term, characteristic polynomial. Okay, so for an LTI system of this form, there are two solution types. Actually, three. But I'll give you the first two solution types first. So the first solution type is the homogeneous solution. Has anyone heard this term before? Okay. So the homogeneous solution is essentially the component of the solution that depends on the system's initial conditions. Okay, so it's the response of the system when the input to the system is 0, but there is a non-zero initial condition. Okay, so we can write that as our input u is equal to 0, and our initial condition is non-zero. Okay, so this is, like I mentioned before, it's the component of the solution that depends on the system's initial state or boundary states, as we'll see in a little bit. Okay, the second solution type is the particular solution. And this is the solution corresponding to the particular input to the system u. Okay, so in this case, our input u is non-zero, and we won't consider the initial conditions. So we'll consider the initial conditions essentially to be 0. So the initial conditions don't factor into this solution. Okay, so we have the homogeneous solution corresponding to the initial conditions. We have the particular solution corresponding to the input that the system is forced with. And we also have the complete solution, which is simply the homogeneous solution and the particular solution added together. Okay, so it accounts for both the homogeneous component of the response and the particular component of the response. So I'll just write incorporates both. And for an LTI system, the complete solution is equivalent to simply adding the homogeneous response and the particular response together. Okay. All right. Are there any questions on the different solution types and what they mean? Any questions? How many of you are familiar with this terminology? Is this something you encountered in undergraduate? Yeah. Okay, great. Okay, so let's look at how do we solve LTI systems like this? First, let's take a look at just the homogeneous case, because this is simpler to think about it first, and it'll provide some necessary context for when we look at the particular solution. Okay, so what is our strategy for solving a homogeneous LTI differential equation? What is our strategy for solving this equation here? Any ideas? So, right. So, I think I kind of get what you're getting at here. Essentially, what we're doing when we're solving for this differential equation is we need to find y. First, let's just consider it without u. So we're just going to be looking at this differential equation, but with the right-hand side equal to 0. And what we're trying to do is we're trying to find a function y that when you plug it in, the left hand and the right-hand side are equal to each other. So let's just assume a form for what y is going to be and see what happens. Okay. In particular, let's assume that y is of the form yt is equal to e to the lambda t, okay, where e to the lambda t is the exponential function. Lambda here is just some constant, and t is our time variable. Okay, so let's assume that the solution takes this form. Okay, what will the first derivative of this solution be with respect to time? Right, it'll be lambda times e to the lambda t. Okay, and similarly, what will the second derivative be? Right, it'll be lambda squared e to the lambda t. And if we go all the way down to the nth derivative, you can see the pattern. You will get lambda n e to the lambda t. Okay, so let's go ahead and write out the homogeneous form for that generic LTI system. And let's plug in this solution and see what happens. This is going to be kind of an exploration. We don't know what we're going to find yet. Okay, so let's write out the homogeneous form of the LTI system. The nth derivative of y with respect to time plus a n minus 1, the n minus 1th derivative of y with respect to time, and so on, plus a1 dy by dt plus a naught y is equal to 0. Okay, we're just looking at the homogeneous case right now. We're not going to worry about the input yet. That'll be next time. Okay, so let's go ahead and plug in our solution y into this equation and see what happens. What will this first term become? All right, so this will be lambda to the nth power times e to the lambda t. All right, very good. Okay, and this next term here, right? So we'll have this first coefficient, a n minus 1 times lambda to the n minus 1 e to the lambda t, and so on and so on. Here we'll have, what will this term be? This term right here, right? Okay, lambda e to the lambda t, and then this term here will simply be a naught e to the lambda t is equal to 0. Okay. So looks like we're getting somewhere. Now note that all of these terms over on the left-hand side are multiplied by e to the lambda t, right? So we can go ahead and we can factor that out. So we'll have lambda to the n plus a n minus 1, lambda to the n minus 1, and so on, to a1 lambda plus a naught, all multiplied by e to the lambda t is equal to 0. Now, is it possible for this term here to be equal to 0? Is it possible for e to the lambda t to be equal to 0? No, right? Only if one of those variables is negative infinity, right? So we can just not worry about this term here. Let's just divide through by e to the lambda t. It won't affect the solution. And what we'll end up with is the following polynomial, lambda to the n plus a n minus 1, lambda to the n minus 1, plus dot, 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 plus a1 lambda plus a naught is equal to 0. Okay, so we have a polynomial set equal to 0, right? How can we solve this equation here? Right, we have a polynomial set equal to 0. First of all, how many solutions are there to an nth order polynomial? N solutions, right? So finding the solution to our LTI system is equivalent to finding the n different roots of our characteristic polynomial. Okay, so let me write that out. Finding the solution to the LTI system is equivalent, it's the same thing, to finding the n roots of the characteristic polynomial. Okay, very good. And just as a quick note, this equation here is the exact same as the denominator here. So this is the same as the characteristic polynomial. I just wanted to point that out. Okay. Okay. Are there any questions about how I arrived at this solution procedure? Okay, so essentially the solution procedure is assume that your solution is of the form e to the lambda t, where lambda is some constant. If you substitute that solution into the differential equation, you will arrive at a polynomial with respect to lambda. And the objective is to find the n roots, the n values of lambda that satisfy this polynomial. Okay. Now, if you find a root of this equation, is that solution unique? No, right? So there's n different roots. And what else do we know about linear differential equations, right? Something on your homework. Essentially, any linear combination of these solutions to the LTI system is also a solution. Okay, so this is an important theorem. I will write this out for you. Okay, so if we have solutions to our LTI system, Z1 is equal to E lambda 1t, so this corresponds to one root of that characteristic polynomial. Z2 is equal to E lambda 2t, corresponds to another root of the polynomial. And Zn is equal to E lambda nt, which corresponds to the nth root. if these are all solutions to a linear homogeneous differential equation, then any linear combination of these solutions is also a solution. Okay, so this is a really important result. Writing this out mathematically, we have that YT, our solution, is equal to any linear combination of these different solutions. So YT is equal to C1 e to the lambda 1t, where C1 is some constant, can be any constant, plus C2 e to the lambda 2t, and so on to Cn e to the lambda nt. Okay, so if we have solutions corresponding to the different roots of our characteristic polynomial, any linear combination of those solutions is also a solution to the differential equation. Okay, so for a real world physical system, we know that there is a unique solution corresponding to that system's response, right? If you take our structural system and you disturb it, at the first time step. So if you simulate the homogeneous response to that structural system, it'll always give you the same response, right? It's not like it's randomly picking different solutions. So how do we determine the values of these coefficients? How do we constrain our solution so that it corresponds to the real world physical behavior? Right. So in order to specify a unique solution to our LTI system, we need n boundary and or initial conditions. Okay, so I'll write to specify a unique solution, we need n as in November boundary or initial conditions. Okay, so it sounds like this is, many of you remember this from your undergraduate differential equations. This is an important concept. Okay, so we'll be dealing with two different types of problems in this class. There are two main types corresponding to the different conditions that you give to constrain the solution. The first are boundary value problems. And the second are initial value problems. Okay, so you might see these abbreviated as BVP or IVP. But essentially, these correspond to the different initial and or boundary conditions you give to specify a unique solution to the problem and determine those coefficients C1 through Cn. Okay, so for a boundary value problem, you essentially pick, assuming that your variable t represents time, you pick n different points in time and you specify the value of the solution at those points in time. And with those n different conditions, those n boundary conditions, you can specify a unique solution to your LTI system, right? So we'll assume, for instance, that y at time 0 is equal to some known value y naught, y at time 1 is equal to some known value y1, and so on to y at time n minus 1 is equal to y n minus 1. So note that this is n different equations from 0 to n minus 1. Okay, so for the boundary value problem, you essentially pick different points, pick n different points that your solution has to pass through. The other form that we'll be dealing with primarily in this class are initial value problems. Okay, so this is probably what you're more familiar with seeing. And for an initial value problem, you essentially specify values of the output and its derivatives at the first time step. Okay, so we will have, for instance, the value of the output at time 0 is equal to y naught. The first derivative of our output at time 0 is equal to some known value y naught dot, and so on, all the way to the n-1th derivative of y at time 0 is equal to some known value y n-1 at time 0. Okay. Are there any questions on initial versus boundary value problems? Is this something that you've maybe seen before in undergraduate? Okay, great. I know I'm starting off a little bit slow, but I want to make sure all the concepts are clear before we start moving into more challenging subjects. Okay, great. Any questions? All right. So last time I told you that the response of the system can be examined in terms of what the roots of the characteristic polynomial are, right? And I showed you, for instance, that for certain roots, the behavior of the structure would essentially behave as a harmonic oscillator that oscillates forever. For other values, you may see an oscillator that becomes damped. So what I want to do now is I want to show you the different cases for the roots of the characteristic equation and what the response corresponding to those roots looks like. Okay, so there's 4 basic cases I want to show you. Every LTI system's response basically consists of different linear combinations of these 4 different responses that I'm going to show you. Okay, so if you know what the individual responses for each of these roots are, all you have to do is add them up to get the total response of the system. So any LTI system behaves as some combination of these 4. Okay, so let's look at the roots of the characteristic equation. Okay, so first, let's look at case number 1. Okay, we're going to look at a root lambda I that is real. So lambda I is in the real numbers and distinct. In other words, lambda I is not repeated. There's only one root with the value lambda I. Okay, the response corresponding to a root that is real and distinct will be of the form yi of t is equal to e to the lambda I t. Okay, so if you have a root that is real and distinct, the component of your response corresponding to that root will be the exponential function evaluated at lambda I t. Okay, so what does the response corresponding to this case look like if lambda I is real? Exactly. So the response corresponding to a root of this form will be either exponential growth or exponential decay. So let's draw it out. We have yi of t, t, yi of t, t. Okay, so if our lambda is positive, if it's greater than 0, if lambda is greater than 0, you will get exponential growth. Okay. If lambda is negative, you will get exponential decay. There's also another case that I neglected to mention here. What's the third case? Lambda is equal to 0. What will your response be in that case? 1, right? You'll just have a constant of 1, which is possible. Okay, so very good. Great, let's go on to the second case. This is kind of the tricky case, and it will arise sometimes. Case 2 is when you have roots lambda I that are real and repeated. Okay, so in this case, for each root, repeated m as in Mike times, you will get a response of the form yi of t is equal to e to the lambda it plus t e to the lambda it plus, and so on, all the way to t time to the m as in Mike minus 1 e to the lambda it. Okay, so you'll essentially get these exponential terms weighted by time. So note that this is not a plus here, this is a t, and this is a t as well. Okay, so what will the response look like for this case? Let's look at the case for lambda as positive and lambda as negative. So first, let's look at the positive case. What'll the response kind of look like? And you don't have to describe exactly what it'll be, but what'll it look like for lambda I greater than 0? What will the response look like? I know it's hard to specify exactly, but essentially it'll look very similar to the exponential growth case from before. You'll have exponential growth that is scaled by time. So actually this should begin at, well, it won't necessarily begin at 0, but you'll get exponential growth that gets scaled by time. And what about for the negative case? What about for the case of lambda I less than 0? So it'll decay, but it will also jump up at first. Yeah, so you'll get something that looks kind of like this. And don't treat this as an exact drawing. Actually, I'll draw it in blue here to be consistent. Don't treat this as an exact drawing, but it'll look something like this. And this is for lambda I less than 0. So you'll have the decay, but weighted by the time term. Okay, very good. Okay, so the third case is a particularly important case to talk about. And this is the case of lambda I in the complex numbers as conjugate pairs. Okay, so remember, when we're finding the roots of the characteristic equation, sometimes we will get roots that have an imaginary component. Sometimes we'll get imaginary roots, right? That affects what the response of the system will look like. So those imaginary roots will appear in pairs. So it's possible that we'll get roots that take the following form: lambda I is equal to a plus bj, where j is the imaginary unit, so square root of -1. Okay, and the response we can write the same as before for case 1. We have that the response is equal to e to the lambda I t. We can separate out that lambda I, so we get e to the a plus bj times t. Let me write this as ai bi. And this we can separate out due to the properties of exponentiation. We can write this out as e to the ai times e to the, I'll just write it as j bi t. Okay, so these are both multiplied by t. Okay, so this is a little bit cumbersome to deal with. We can simplify this a little bit to gain some intuition about how the response will look like. In particular, we can use Euler's identity. I'm still not exactly sure how to pronounce Euler's name. I'll just say Euler. We can use Euler's identity. And does anyone remember what Euler's identity is? Yeah. Yes, yes. So essentially, we can take this term here with the imaginary unit in the exponent, and we can write e to the bj is equal to cosine b plus j sine b. Okay, so our response, let me go ahead and create a new page real quick. I'll just give you a second to write it down. But our response will essentially incorporate these harmonic components, these trigonometric components. Okay, so we have that yit is equal to e to the ait times quantity cosine bi of t plus j sine bi of t. Does this look familiar to material you may have seen in undergrad? Right. So we can take that exponent with the imaginary unit in it, and we can express it as cosine bit plus j sine bit. Okay. So essentially what we have here is we have two different components of the response. This component here represents the harmonic response. Okay, so this is what's going to determine the oscillations we see in the response. So if you see oscillations in your response, this term is what's determining those oscillations. And this component here, I'll just call it the magnitude, although that term is probably a little bit imprecise. It essentially defines the growth or decay that is applied to that oscillatory response. Okay, so if AI is positive, then you will have an oscillatory response with exponential growth. If AI is negative, you'll have an oscillatory response with exponential decay. Okay, you have a question?
Would we ever, like in civil engineering system, see a response with a positive magnitude?
So we will be talking about that when we get to controls, because it's possible that we can create a response like that that makes the system unstable, right? And typically you may see a response that is unstable, but it eventually will reach some saturation point at which our linearization breaks down, right? And it'll no longer grow forever, right? It'll saturate at some point. So you will later on in this class encounter systems that exhibit exponential growth. We want to try to avoid that most of the time. Yeah. Great question. Okay, so what will the response of a system like this look like? There's three different cases. Okay, so let's think about what the response will look like for these three different cases. Okay, so let's think about the case where AI, so let me put this should go down here. Okay, so this is y-axis is yi of t, x-axis is t time. So first, let's think about the case where AI is equal to 0. What will the response look like if AI, the real component of the root, is equal to 0. What will this term become here? 1. And so you'll end up with just the harmonic component, right? So you'll get a pure sinusoid. Remember, we saw this when we looked at the spring mass system. Okay, let's look at the case of AI greater than 0. What'll your response look like if AI, the real component, is greater than 0? Right, exactly. So you'll get exponential growth, but you'll also have this oscillatory component. Right, so you'll get exponential growth with oscillation. And if AI is less than 0, you can see where the pattern is going, but let's just say it. What happens when AI is less than 0? Yeah, you'll get an oscillatory response with decay. Very good. Okay. And very quickly, let's just close off the final case. I mentioned that there are 4 cases. The final case, which we won't really be dealing with in this class, is the case of roots that are complex and also repeated. Okay, in this case, the response is the same as case 2. So you'll have e to the lambda I t plus t e to the lambda I t plus so on and so on all the way to t n minus 1 is in November e to the lambda I t. So it'll be the same as case 2. Except lambda I is complex. So there'll be both a envelope shaping term and an oscillatory term. Okay. Are there any questions on the different response types that I presented for you today? Okay. So key takeaway points here. The response of any LTI system is some linear combination of the 4 different cases that I've shown you here. All right. So when you're solving an LTI system, you solve for each of those roots, you determine those individual responses corresponding to each roots, and then you add them together. And that will give you the ultimate response of the LTI system. Okay. Similarly, another important point, the real component of the root determines its exponential growth or decay. And the imaginary component determines what? Right, so it's harmonic behavior or it's oscillatory behavior. If you have an imaginary component in any of your roots, you will get some oscillation. Otherwise, you will not. Okay, so that's essentially all the information you need to know what the response of an LTI system is going to be like. It's completely determined by the roots. Oh, I should note that this is for the homogeneous case only. We'll get to the case of inputs in the next class. But for the homogeneous response, it will essentially be some combination of these 4 cases. Okay, any questions? No? All right, so let's go through a couple examples. I'm going to take you through an example of essentially solving the homogeneous response for different LTI systems. So first, we're going to take a look at a simple first order system. This will just be a simple test case that we're going to look at to test our concepts. Doesn't really correspond to anything in the real world. So we'll have our first order system. Let's just say that it's dy by dt plus ay is equal to 0. Okay, so this is a homogeneous system. There's no input term here. And let's say that we have an initial condition specified. How many initial conditions do we need, by the way? 1. And how do we know that? right? So there will only be one root of this characteristic equation. So we only need one initial and/or boundary condition. So very good. Our initial condition, let's just say that it's equal to 2. Okay, so let's put this into practice. So what do we do to find the solution to a system like this? Oh, well, we could do that. We could do that. But let's do it in the way that we presented in class today, just as an exercise. So let's find the roots of the characteristic equation. Okay, so we take the system and put it in operator form. What will it look like? What will this first term become? Using our convention from last class for operator form. Yeah, it would be py plus ay is equal to 0. Okay, so remember that in operator form, it'll put the system in a form that is equivalent to the characteristic polynomial that we're trying to find, right? Okay, so we can factor out y. We get p plus a all times y is equal to 0. And we need to find the root p that solves this equation. So what will the root p be equal to? Right, so p will be equal to negative a. Okay, are we done? No, we haven't used this piece of information yet. Okay, so let's go ahead. So we know that our solution corresponding to this root will be of the form, I'll write it over here, yt is equal to c, some constant, I'll call it c1 e to the negative at, because negative a is our root. Okay, and how can we find this value for c1? Exactly. Okay, so we'll be using our initial condition. We know that y at time 0 has a known value equal to 2. So we'll evaluate this equation at time equal to 0. So we have that y at time 0 is equal to 2 is equal to c1 times e to the negative a times 0. Okay. What does this term here evaluate to? 1. And so we get that c1 is equal to 2. And the ultimate response that we get is 2 e to the negative at. Okay, wasn't so bad. Okay. And a quick quiz, what will the response look like here? What will the response look like? Okay. What will the response be at time 0? 2. And what will the response over time look like? Yeah, it'll be exponential decay. So for a first order system, you can only have exponential growth, exponential decay, or a constant response. Okay, are there any questions on this process? All right, let's spice things up a little bit. Let's see, you're getting ready. Let's take a look at a real world problem. So let's go back and look at our structural system without damping. Let's take a look at the case without damping. First, during the last lecture, I told you that the response for the structural system without damping will oscillate forever. Here we are going to confirm that that is the case. Okay, so we have our structural system just as before. You have a beam or a story supported by two pillars or two beams. Okay, the structure has some mass M and some stiffness K. Does not have any damping. Okay. And we're just going to be looking at the homogeneous response of the system. So there's not going to be any force input. Instead, we're going to assume that the structure has some initial deflection. As the structure has some initial deflection x naught. So let's say the structure was displaced and we're just letting it go. Okay. That's the response that we're going to simulate here. Okay, we know that the dynamical equations that describe the motion of the system are given by Newton's second law. We have mx double dot plus kx is equal to 0. Okay, this is just coming from Newton's law. And let's specify our initial conditions. How many do we need here? How many initial conditions would we need here? 2, right? Because it's a second order system. So let's say that the initial displacement is equal to some known value x naught. And let's say that the initial velocity is 0. Okay, so we were simulating if we displace this structure over to the right, let it go, what is its response going to look like? This is the homogeneous response of the system. Okay, so let's do the same thing that we did before. Let's find the roots. Okay, what will this system look like when we put it in operator form? Yep, so we'll have mp squared x plus kx is equal to 0. Can factor out the x, and we get mp squared plus k all times x is equal to 0. Okay, and so now we have to find the roots in P. So how can we do that in general? All right. So let's kind of just apply the general case here and look at it using the quadratic formula. Okay, so yes, you will be using the things you learned back in middle school. What is the quadratic formula? Anyone want to volunteer to shout it out? Very good. Very good. Wow. Okay, so you're right. It's negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so in this case, we have that b is equal to 0. Okay, so this term here will also be 0 minus 4. Our a term is m, and our c term is k. And this will be all over 2m. Okay, so this term in here will evaluate to 2mk. Wait, sorry, did I do that right? Yeah. Okay. So let's go and write this out. So this will be equal to plus or minus square root of negative k over m. Right? Yep. As if, yeah, square that one. Yeah. Negative k over m. And we can factor out this imaginary unit so that we get that the roots are equal to plus or minus j times square root of k over m. Okay, so our roots are completely imaginary. There is no real component. So my assertion to you is that that will result in a harmonic response with no decay. Let's see if that turns out to be true. Okay, so let's go ahead and look at the prototype solution. So we know from the cases of the different roots I gave you that the response of a system like this will look like the following. Xt is equal to e to the at times quantity c1 cosine bt plus c2 sine of bt. Note that I've just included that imaginary unit in this constant here. That's where it went. Okay. And we know that, right? We know that the real component is 0. So let's go ahead and just substitute both the real and imaginary parts of this root into this equation. We have that our A component, so A is going to be equal to 0, and B is going to be equal to the square root of k over m, right? Okay, so let's go ahead and substitute those in. We have that xt. What does this evaluate to? 1. Okay, so we'll end up with c1 times cosine square root k over m times t plus c2 times sine square root k over m times t. Okay, so are we done? No. We have to determine the coefficients c1 and c2 by using our initial conditions. Okay, so let's take a look at the initial displacement condition first. Okay, so this equation will become, let's say, let x at time 0 equal x naught, and let's evaluate and see what we come out with. So this term here will become our known value, our known initial displacement x naught. Here we will get c1 times cosine of square root k over m times 0 for time equal to 0, plus c2 times sine square root k over m times 0. Okay. What happens to this term? This goes to 0. What happens to this term? This becomes 1. Okay, and so what we end up with is x naught is equal to c1. Okay, very good. All right, now what do we do now? Right, so we need to use our other initial condition on the velocity. That means we have to do what to this original equation here? Yeah, we have to differentiate it. Okay, so let's go ahead and do that. If we differentiate this equation, what we get is x dot t is equal to negative square root k over m sine square root k over m t. Sorry, this should be times c1. Let's write like that. Plus c2. Did I write that right? Yeah, I have cosine first. Okay. C2 square root k over m cosine square root k over m t. Let me just check and make sure I got that right. Yes, I did. Okay. So now what we need to do is we need to plug in our initial condition for the velocity at time 0. So this expression here is equal to x dot at time 0, which we know is equal to 0. It's equal to negative c1, we know already is x naught. Let's go ahead and write that. Okay, so we get negative x naught times square root k over m sine square root k over m at time 0 plus c2 square root k over m cosine square root k over m time 0. All right. And what does this term here evaluate to? 0. You all know your trigonometric identities. And this one here evaluates to, right, so just this cosine term here will evaluate to 1. And we get that 0 is equal to C2 root K over M, which means that, what is C2 equal to? C2 is equal to 0. Okay, very good. All right, so what does our final solution for the response look like? We get that x of t. We go back here. We have that x of t is equal to c1 times cosine square root k over m times t plus c2 sine square root k over m times t. This component goes away because c2 is equal to 0. c1 is equal to x naught. And so our solution is equal to x naught cosine square root k over m times t. So this is the response corresponding to our initial displacement. This is the exact solution. So if you displace the structure by some amount x naught and let it go, this is the exact response you will get. And as I asserted to you in the last class, what's this function going to look like as time goes to infinity? Right, so it's just going to be a purely oscillating sinusoid. There's no decay component in there. Okay, so the response will look like a purely oscillating sinusoid. Okay, so that's an example of how you can solve a second order system. This is for the case where there is no damping. Let's just take a quick look at the case where there is some damping. I'm not going to go through the entire solution procedure, but I want to show it to you just so that you have this information. Okay, so let's consider the same system, but this time with damping. Okay, we have some initial displacement. Okay, and we have now a mass M, stiffness K, and damping C. And we know that the dynamics of the system correspond to the following equation: mx double dot plus cx dot plus kx is equal to 0. And let's use the same initial conditions as before. So our displacement at time 0 is equal to some constant x naught. And our initial velocity, let's set it equal to 0. Okay, so I'm not going to go through the entire solution procedure again, but I want to just look at what the ultimate solution will look like depending on what our damping looks like. Okay, so this you may remember this from undergraduate differential equations as well, but I want to make sure I review this. Okay, so if we find the roots, okay, our characteristic equation will look like something of the form mp squared plus cp plus k all times x is equal to 0. And from the quadratic formula, our roots, we have two roots again, will be of the form negative c plus or minus square root of c squared minus 4mk all over 2m. Okay. So what is the major difference in terms of the roots between this solution and the previous solution that we just saw? Yes, so we now have a real component. Okay. We now have a real component, which means we will have that exponential decay term in this case, given that C has to be positive. damping coefficient is defined to be positive. Okay, so let's look at what the solution will look like. So we know that our prototype solution will be of the form x at time t is equal to e to the at, where a is the real component, times c1 cosine bt plus c2 sine bt. Okay, so we have this real component. The real component is negative because c has to be positive. So let's just make it clear that because we have a negative real component, the structural response will exhibit exponential decay in terms of its magnitude. Okay. Will it always exhibit oscillation? No, Jimmy's saying no. So you may remember from undergraduate differential equations that there's different cases that will determine whether the system oscillates or not, right? So what determines if we'll have oscillation in our system? Right. So you will only see oscillation if your roots have an imaginary component. Is it possible to not have an imaginary component here? Right. So there's a couple different cases. Let's look at the case of, so there's two components in this square root. Essentially, if the term in this square root is negative, you'll get an imaginary component. If it's positive, you will not. So let's just quickly look at those different cases. So if 4mk is greater than c squared, what will happen? If 4mk is greater than c squared, right, you'll get oscillation. This system will be what's called underdamped. The terminology I don't think is that important, but you will essentially what you'll see is you'll get oscillation. Okay, what about for the case where 4mk is less than c squared? Right, so in this case, you will be overdamped. Okay, so you will not get no oscillation. There won't be an imaginary component. You won't see any oscillation. All right, there's actually one more case. You can probably guess what it is. If they're equal, what happens? Critically damped, but what does that mean? So what happens to our roots if it's critically damped? You'll have two roots, all right? Right. So it'll correspond to that case 2 that we talked about, right? So let's just go through it just to make sure everyone's on the same page. This term inside here will evaluate to 0. And so you'll have P1 and 2, our roots, are both equal to negative C over 2M. So they're not conjugate pairs. They're two roots that are equal. And they're both real. So what you'll get is a response corresponding to that case 2 that I showed, where you'll have a solution of the form TE to the lambda t. Okay. Great. Are there any questions on the different types of responses you can see for second order systems? So I just want to make okay, first of all, before I interrupt, are there any questions on this last module that I showed here? So a lot of this should be review from undergraduate differential equations, and that's fine. Note that these terms here, underdamped, overdamped, critically damped, and so on, these come from the domain of mechanics. And so they're usually thought about in terms of, mechanical systems, spring mass damper systems. But to be clear, all of these cases apply to any system with second order type behavior. So it doesn't matter if you're talking about a chemical system, electrical system, all three of these conditions apply no matter what second order system you're looking at, second order or higher. Okay, so it's not just for structural problems. This is for every LTI system. Okay, great. Well, I don't have enough time to talk about particular solutions. I'll get to that next time. What I do want to talk about, though, is I quickly want to just discuss discrete time systems. I didn't get to it last time. So let's just quickly talk about discrete time systems. And the behavior of discrete time systems is analogous to continuous time ones. So, for continuous time, systems, our solutions corresponding to our individual roots of the characteristic of equation will be of the form e to the lambda it, right? For discrete time systems, it's almost the same, but just a little bit different. You'll have the solution corresponding to the root is equal to lambda I to the kth power. Okay, so instead of using the exponential function, it will be the root evaluated to some exponent. Okay, so just keep this in mind. When you're working on discrete time problems, the logic is analogous, but the actual form of the root itself will be slightly different. Okay, and let's just go through an example of a discrete time system because I didn't get to it last time. And I just want to make it clear. Forgive me if I go 1 minute over time. So let's consider an infectious disease, unnamed infectious disease, for which every infected person infects 2 other people each day. How many total people, Y, so the number of total people is Y, are infected after N is in November days? Okay, so we can kind of look at this system in a brute force fashion. Let's look at the number of people infected after the first day. So this will be Y at time index 1. So from our description of the problem, we have the number of infected people after the first day is equal to the number of infected people at the beginning of the first day, Y0, plus 2 times the number of people infected at the beginning of the day, right? Because on each day, each person infects 2 other people. Okay, so what you'll end up with is the number of people infected after the first day is equal to 3 times Y0. Okay, let's look at the second day. Okay, the number of infected people will be equal to the number of people infected after day 1 plus 2 times the number of people infected after day 1. Okay. Which will be equal to 3 Y1, okay, which is equal to 3 squared Y0. Okay, the number of people infected at day 3 will be equal to the number of people infected at day 2 plus 2 times the number of people infected at day 2, which is equal to 3 times the number of people infected at day 2, which is equal to 3 cubed times the original number of people infected. And you can see if you continue on in this pattern, the general solution for this discrete time system will be the number of people infected at day K is equal to, 3 to the K times the original number of people. Okay, so when you're working with discrete time systems, instead of the exponential function, you will get your root evaluated to some exponent. Okay, so very good. That's all I have time for today. Thank you for sticking around, and please come to office hours tomorrow at 12 if you have any questions. Great to see you, and cheers.